Hello dear students, this is grade 11 mathematics lesson on unit 7, the set of complex number. In this lesson, we focus on simplification and polar representation of complex numbers. So, after completing this lesson, you are expected to simplify some complex numbers and some complex number expressions to their simplest form and represent the complex numbers in polar form. So now let's continue to the lesson. So let's see first the definition of a set of complex number. A complex number Z is an expression written in the form x plus yi for some real number x and y, and where this I is the square root of -1, or in other words, you can see here where I squared is equal to -1. I can write this to their equivalent. Okay, so the number x, this number x, we call it the real part of the complex number, and it is denoted by real part of z. We can write like this. And the number y is called, this y, the number y, we call it the imaginary part. It's a coefficient of imaginary number, so we call it the imaginary part of z. And it is denoted by m of z. So the set of complex number, it is denoted by this symbol. This symbol is denoted by this symbol. We say it is a complex number. So this set of complex number is defined as it is the form of x plus yi, where x and y are real numbers and I is equal to the square root of -1, or I squared is equal to -1. So now let's see this example. The complex number z here is given to be, it is 3 minus y. So let's find the real part and the imaginary part of this complex number. As you can see easily, the real part of this complex number is this 3. Real part of z is this 3, and the imaginary part is a coefficient of imaginary I, so it is -2. So the imaginary part is, it is -2. Now let's see this one, complex conjugate and modulus of a given complex number. Z bar is equals to x minus yi. Simply you take the opposite of the imaginary part, x minus yi. Okay, now let's see about modulus. The modulus or absolute value of a complex number z is equal to x plus yi. It is denoted by absolute value of z, and it's given by this one. The modulus of z is equal to the square root of real part plus the square of imaginary part. So this is it. Now let's see example for this. Take this one. If z is, if we are asked to find z bar, simply the complex conjugate of this number, you take the opposite of the imaginary part, so it will be this 5 minus 2i. Now let's see this example. If z is equal to 4 minus 3i, then find the modulus of z. To find the modulus of z, the modulus of z, this is equal to the square root of the square of real part. The square of real part is 4 squared plus the square of the imaginary part, it is -3. We do not include I, by the way. You have to be careful with this. I is not included. Simply take the imaginary part number only. So it is -3 squared. Therefore, this equal to the square root of 4 squared is 16, and -3 squared is 9. This result is square root of 25. The final answer will be this 5. Therefore, the modulus of this number is, it is 5. Now let's see the simplification of complex numbers. Evaluate 3 minus 2i over 4 plus 3i. You are asked to simplify this expression. To simplify or to divide a complex number, what you do is simply you multiply both the numerator and denominator by the complex conjugate of the denominator. So let's see this. Therefore, here solution 3 minus 2i over 4 plus 3i. This is equal to, you multiply by conjugate, therefore here it is 3 minus 2i divided by 4 plus 3i, you multiply it by the complex conjugate of the denominator. Therefore, this equal to, it is 4 minus 3i divided by 4 minus 3i. So, now let's simplify this. This multiplies this one, therefore, applying distributive property, 3 multiplies 4 minus 3i and minus 2i multiplies 4 minus 3i divided by the product of these two is simple, by the way. Simply, if you remember, x plus y times x minus y is given by, it is the difference of two squares. It gives you this one. Therefore, the product of these two is this, the difference of two squares. So, it is 4 squared minus 3i squared. Therefore, this equal to 3 times 4 is 12 minus 9i, and the product of these two it is minus 8i minus 2i times minus 3i becomes, the negative cancels, 6 times I squared, 6i squared, 6i squared. Since I squared is negative 1, here it will be minus 6 divided by, this result, it is 16. This 9, I squared is minus, so it becomes plus 9. Therefore, this equal to, simplifying this, minus 9i and minus 8i, taking the imaginary part, minus 17i. This is minus 17i. 12 minus 6 it is positive 6. 12 minus 6 is positive 6 divided by, it is 25. So, this is a simplified answer, or you may write this in this form. Negative 17i divided by 25 plus 6 over 25. So, this is how to simplify complex number, or how to divide a complex number. Okay, now let's continue to the second example. Example 2, we are asked to find or to simplify I to the power of 20 minus I to the power of 100 plus I to the power of 15 plus the square root of negative 4. Now let's do this together. Solution. I can write, or let me write the question again, I the power of 20 minus I the power of 100 plus I the power of 15 plus the square root of negative 4 is given. So, this is equal to, I can write this in this form, I the power of 2 the power of 10 minus this part, it is I the power of 2 the power of 15. because 50 times 2 gives you 100, 10 times 2 gives you 20. Plus, I can write this, I the power of 14 times I, plus I can just evaluate the square root of negative 4. The square root of negative 4, this is the square root of negative 4. This is equal to, it is the square root of 4 times negative 1, or the square root of negative 1. Therefore, the square root of 4 is this 2, and the square root of negative 1 is I. This it is 2I. So therefore, the square root of negative 4, it is 2I. So this equal to I squared is minus 1. Therefore, it is minus 1 the power of 10 minus. Here also, I squared is minus 1. That is the power of 50 plus. I can write this I the power of 2 the power of 7 times I. And we have here 2I. Therefore, here this equal to negative 1 the power of 10 is, it is 1, minus negative 1 the power of 15 also it is 1, plus I can take this one. This one is this negative 1. Negative 1 the power of 7 is this minus. Minus times I is this minus I. Therefore, here I have minus I plus 2I. Therefore, when you simplify this, these two cancels out, and negative I plus 2I is this I. Therefore, the final answer, or the simplified form of this expression is, it is the imaginary number I. Now let's continue. Example 3. We are asked to solve x squared plus x plus 1 is equals to 0 in the set of complex number. So this is a quadratic equation. We can apply a quadratic formula to solve this. So let's do together solution. The quadratic formula, if you remember, x is equal to, it is minus b plus or minus the square root of b squared minus 4ac over 2a. Therefore, x is equal to minus b, the coefficient of b is 1, minus 1 plus or minus the square root of b squared, our coefficient of b is 1. 1 minus 4 times ac. A is 1, c is also 1, 4 times a is 4, so here it is 4 divided by twice of a. The coefficient of a is 1, twice of a is 2. So x equal to negative 1 plus or minus the square root of 1 minus 4 over 2. So here the square root of 1 minus 4 is negative 3. The square root of negative 3 in set of complex number, we can evaluate this. This equal to the square root of 3 times the square root of negative 1. So this equal to, it is the square root of 3, square root of minus 1, it is I. So square root of 3i. Therefore, here x is equal to minus 1 plus or minus the square root of 3i divided by 2. So the solution set for this equation is written in this form. The solution set, this equal to, it is minus 1 plus root 3 I divided by 2 and minus 1 minus the square root of 3 I over 2. So this is the solution set of this quadratic equation in set of complex number. Okay, the next part is, it is polar representation of complex numbers. Suppose, let's derive the formula of polar representation of this complex number. Look, this complex number here, let's have this complex number z, which is equal to this x plus yi. Therefore, here we have an angle theta, and the distance from these two parts is this distance is x, and this distance is y, and assume this it is r, this distance we can find r here using Pythagoras theorem. R squared is equal to x squared plus x squared, so r squared give us the square root of x squared plus y squared. So here, in addition to that, we can evaluate sine theta. Sine theta, it is opposite over hypotenuse, it is y over r. So from this, y is equal to this r sine of y is this r sine of theta. And from cosine cos theta, this is equal to cos theta, it is adjacent over hypotenuse, it is x over r. Therefore, here x is equal to this r cosine of theta. So we have x here, and we can also evaluate theta here. Tan theta, this is equal to this y over x opposite over adjacent, so it is y over x, and theta can be evaluated using this one, tan inverse of y over x. So combining this, you will have this one. We have z is equal to this x plus yi. Therefore, to write this in polar form, z is equal to x is replaced by r cos theta. So this is r cosine of theta plus, and y is replaced by r sine theta. So here I times sine theta. So taking the complex number z is equal to x plus yi is equal to x is here r cos theta, and y is r sine theta. So in place of y we put r sine theta, I times r sine theta. So taking r as a common here, you get r into cosine of theta plus I sine theta. So this is the polar representation of a complex number, where r is a modulus of the given complex number, and we call theta an argument of z. We call theta argument of z, and the particular theta which is found between negative pi and pi, we call it the principal argument. If theta is between negative pi and pi inclusive, we call this the principal argument, and written in this form, the principal capital A R G of z. In this case, the principal argument is found between negative pi and pi inclusive. So this is a polar representation. Now let's see this concept. Okay, so the polar representation, as we said, it is z is equal to r into cos theta plus I sin theta, where I said r is the modulus of z given by this form, and theta is this, it is the angle formed with the vector of z with a positive x-axis, we call this an argument, theta, we call it an argument z. It's obtained by tan inverse of y over x. The particular theta, which is found between negative pi and pi, we call this a principal argument. And here, when a complex number is written in the form this, theta, we call it argument of z. I said this one, argument of z, and denoted by this small a, argument of z. And the particular, as I said, the particular theta found between this interval, we call this a principal argument, and written capital A rg of z. Okay. So now let's see example. Express z. Here we are asked to express negative 5 plus 5i in polar form. To write in polar form, we need two things. The first one is R. Solution. R is equal to, it is the square root of negative 5 squared plus 5 squared. So this is equal to, it is the square root of 50, which is equal to 5 root 2. So the next one is finding the argument. To find the argument, you have to be careful. So you need to draw the complex number in a graph, and then you have to identify its quadrant, the quadrant where the complex number found. So here, negative 5, here this is a real axis, it's a real axis, it is 1, 2, 3, and so on. Negative 5, we have negative 5 here. And 5i is here, it is imaginary axis, 5i. Therefore, this is our complex number. Our theta, as I said earlier, it is the angle from positive axis to the vector of this complex number z. So to find this, I need to find this angle first. This angle, to find this angle, simply you take this one. The length of this side is 5. The length of this side also is 5. Therefore, tan theta, simply taking the magnitude, taking this triangle, tan of theta, assuming theta is this one, tan of theta is equal to this. Opposite side is 5, the length, and the adjacent side length is also 5. I'm taking the magnitude only. Therefore, tan theta is 1. From this, you can see that theta is this 45 degree. Theta is 45 degree. But our argument will be not this one. It is a degree is, it is from positive axis to the vector of the complex number. Therefore, this angle will be, it is, since this the total is 180, this angle will be, it is 135 degree. Therefore, our argument theta is, it is theta is equal to this 135 degree, and I can write this in radian form. When you convert this in radian form, you have this 135 times pi over 180. So this is equal to this. By 45 we have 3 45s, and by 45 we have 4 45. So this is the argument of this complex number. Therefore, z is written in this form. Z is equal to this r into cos theta plus I sin theta. Therefore, here this is equal to, we have found r to be this 5 root 2 here. So 5 root 2 into cosine of theta is, it is cosine of theta is 3 pi over 4, cos of 3 pi over 4 plus I sin 3 pi over 4. By the way, you can write this in general form, since sine and cosine are periodic, a pair of 2 pi. So equivalently, this can be written in this form: 5 root 2 into the cosine of 3 pi over 4 plus twice of n pi plus I sine of 3 pi over 4 plus 2n pi, where n is integer. Therefore, this is the polar. I can use this one or this one. Therefore, these are the polar representation of this complex number z is equal to negative 5 plus 5i. Now, note the following. If two complex numbers written in polar form are given, z1 r1 cos theta 1 plus I sin theta 1 and z2 r2 times cos theta 2 plus I sin theta 2, then the followings are true. 1. The product of these two complex numbers in polar form is equal to the product of their modulus times cosine of the sum of their argument. Cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. And z1 over z2, this is equal to, it is the ratio of their modulus times cosine of the difference of their argument theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. And we'll have this one also. z1 the power of n, this equal to it is the n's power of it is modulus times cosine of n times its argument theta 1 plus I sine n theta 1. So this is very important formulas. Now let's see example for this. Now we are asked to simplify 1 minus I the power of 10. To simplify this, multiplying 1 minus I 10 times is very difficult. 1 minus I times 1 minus I 10 times is very difficult. So the easiest way to simplify this one is you need to write this in polar form, so that it will be simple to simplify it. Let's see this. So solution. The polar form of 1 minus I, this is equal to r is 1. The modulus of this one, it is 1. The modulus of, let's do it here. The modulus of this one is the square root of 1 squared plus negative 1 squared is equal to this, the square root of 2. And its argument, I need to draw the quadrant which is found. 1 minus 1 is here, minus I is here, so it is a fourth quadrant angle, and so I need to find this angle. So from positive x-axis to the vector of this complex number. Therefore, the magnitude of this one is 1, this one is also 1. Tan of theta opposite over adjacent will be 1, so it will be 45 degree anyways. Tan theta, if you assume this theta, tan of theta is equal to 1, so theta is 45 degree. But this one is measured from positive x-axis to the vector in clockwise direction, so our argument will be it is negative in the clockwise direction, so it will negative 45 degree. It is negative 45 degree. Therefore here the polar representation of this will be, it is root 2 into cosine of negative 45 degree plus I sine of negative 45 degree. So we are asked to find 1 minus I the power of 10. So this equal to this the power of 10, root 2 times cosine of negative 45 degree plus I sine of negative 45 degree, the power of 10. So this equal to as we put earlier the formula, z to the power of n is equal to r to the power of n. The modulus will be taken as a power and the argument will be multiplied by the power. Therefore, this will be the square root of 2 the power of 10 times this will be cosine of negative 450 multiplied by 10 n theta. We derived the formula. We have seen the formula, and plus I sine of negative 450. Therefore, this is equal to root 2 the power of 10 means it is to the power of 1 over 2 the power of 10. 1 over 2 times 10 is 5. So, this will be 2 the power of 5 times, to find these two angles, these are quadrantal angle negative 450. Let's see this one. So, here negative 450 means you take in a clockwise direction. This is this part negative 360, and then, so let me draw it again. This is negative 360, and then when you add this part, this will be negative 450 degree. Therefore, the coordinate of using unit circle, the coordinate of this part is 0, negative 1, and the first coordinate is the value of cos. This is the value of cos, and this one is the value of sine. Therefore, here cos negative 450, cos negative 450 is 0. This part is 0, and times I times sine negative 450 is negative 1. So, here we have negative 1. When you multiply this, you get negative 32i. So, this is the final answer. So, to summarize what we have seen today, look, the first one, we have defined complex number. The set of complex numbers is denoted by this symbol and given by x plus yi, where x and y are real numbers and I is equal to the square root of negative 1, or I squared is equal to negative 1. And the other concept we have seen today is a complex conjugate. The complex conjugate of the complex number x plus yi is given by taking the opposite of the imaginary part. So, z bar equal to it is x minus yi. And we have also seen the modulus of a given complex number. So, the modulus of this complex number is equal to the square root of real part squared plus imaginary part squared. And we have also seen the polar representation of a complex number, xz is equal to x plus yi. It is given by this form: z is equal to this r cos theta plus I sin theta, where r is the modulus of z and theta is argument is given by tan inverse of y over x. So, this is all about today's lesson. So, for you to try, I will give you exercise. Please try to solve this question. It is all about today's lesson. I will give you 1 minute to copy the question. Until next lecture class, goodbye.